Okay, so on the last problem on the recitation worksheet, we have this question about a leg. So it says, you stand on one foot while holding the other leg up behind you. Your muscles, there's a tendon that is attached to your muscle. Your tendons pull on your bone. Your muscle applies a force to hold your leg in this raised position. So we'll model the situation as though it's here. So we say that the leg pivots at the knee joint. So the knee joint is this spot right here. And the tendon pulls on the muscle about 5 centimeters away from the knee joint. And we'll assume that the lower leg and the foot have a combined mass of about 4 kilograms and that their combined center of gravity is right in the middle of the center of the lower leg. And then we're interested in the force that the tendon must exert to keep the leg in this position. We're also interested in the force on the lower leg at the knee joint. And we want to know the direction of the force that's exerted by the upper leg on the lower leg at the knee joint. So there's 3 forces acting on this leg. We have the weight of the leg, we have the force of the tendon, and we have the force of the joint. So the force of the leg, the weight of the leg, we've said to consider it to be right in the middle of the leg. So this is my model of the lower leg. So the knee is up here and your toes are down here. So I'll call that force at the center of gravity of the leg, and that points down. I'm also fairly confident that I have a tendon force over here that's just about 5 centimeters away from the bone joint that points up. Right, the tendon has to point up in order to prevent the leg from falling down. I also have a bone force, which is a force of the bone right here, which I'll assume is either up or down, but I'm not sure whether that bone force points up or points down. But let's go ahead and draw it down. And since we're not sure, we have to pick a direction one way or another, so I picked down. On the posted solutions, I picked up, so you can see 2 different ways of solving it and seeing that it works both ways. So we'll draw that down, and there's our force diagram. Draw some distances here. So this is 50 centimeters, the total length of the leg. Right? The problem says that that's 50 centimeters, and this distance here is 5 centimeters. And that must mean that, geez, this distance from here to here, well, this distance from here to here better be 25, because the center of gravity of the leg is in the middle of the leg, which means that this distance from here over to here is also 25. But if this distance here is 5, that leaves me 20 for the distance between the center of gravity of the leg and the location of the tendon. So we'll go ahead and throw those in like that. Okay, so that's the force diagram for the person's leg. And let's do the static equilibrium problem. So we have our 2 conditions for static equilibrium, one being that the clockwise torques equal the counterclockwise torques, and the other one being that the sum of all the forces equals 0. And as hopefully is becoming routine by now, we're going to start with the torques equation, and then we'll do the force equation at the end. So we need to choose the location of a pivot, and always the good choice for the location of the pivot is to pick the location of a force where you don't know anything about it. And we have 2 of those here. We have a tendon and a bone. So but we know less about the bone because we don't even know what direction it points. So I guess I'll go ahead and put the pivot here at the bone. I think it would work out just fine if you put it at the tendon. But actually, it doesn't matter. Let's put it at the tendon. So we'll put the force at the tendon, and then we have this torque here due to this force, which causes my rod to rotate that way, which is counterclockwise. And this force over here, which would cause my rod to rotate that way, which is clockwise. So my clockwise torque is the bone torque, and my counterclockwise torque is the torque due to the center of gravity of the leg. And we have chosen right here to be the pivot. So I would say that the force of the bone times the distance to the bone times the radius of the bone equals the weight of the leg times the distance to the center of the gravity of the leg. So now I need to plug stuff in. These R's here are distances from our pivot, which we've chosen to be here, to the location of the force. So RB is this 5 centimeters. And so we'll say FB. First I'll solve for FB. So that's F, the weight of the leg, times the distance to the center of gravity of the leg, divided by RB. The center of gravity of the leg, that's just the weight of the leg. And the center of gravity of the location of the center of gravity is here, which is 20 centimeters away from the location we chose as our pivot. So we'll say, instead of mg, I'm just going to plug in numbers here. The weight of the bone, the mass of the bone is 4 kilograms. So to get that to a weight, I'll multiply it times 9.8. So 4 times 9.8 times 20 centimeters, which I'll write as 0.2 meters, divided by R for the bone, the distance from the pivot to the bone, which is 5 centimeters. I plug in all of those numbers and I get 160 newtons. Oops. 156.8 newtons, which I will round up to 160 newtons. Okay. So you can see what would have happened here if we had chosen the force of the bone to point up. If we had chosen the force of the bone to point up, then both of these forces would have resulted in a counterclockwise torque. If this had pointed up, right, if we had drawn this arrow pointing up and I set our pivot right here, then a force pulling up would cause a counterclockwise rotation instead of the clockwise rotation that it causes, which would mean that we had 2 counterclockwise torques and no clockwise torques. And all of our math would have been exactly the same, except that in the end we would have gotten a negative down here. In the end we would have gotten a negative 160 newtons instead of a positive 160 newtons. And this happened also in a class problem that we had done, where if you get a negative number, we don't stress about it. What that negative number tells us is that we've drawn the force pointing in the wrong direction. So it turns out that I drew the force pointing in the correct direction, so 160 newtons, and no force is complete without a direction, so its magnitude is 160 newtons, and we'll say that it points down. Okay, so that is the force on the bone. So I guess that is part B. And also part C is what's the direction of the force at the bone. So that's C right there, points down. And this is why the problem has specifically asked the direction of this, because it was ambiguous what direction you drew it. So we've done it here, and it's not ambiguous anymore. Okay, we are almost done. We have the force of the bone, and now we need the force of the tendon, and we will use, what part is this now? A, I guess. We will use Newton's first law to solve that. So let's say that the sum of all the forces equals 0, which means that the tendon is the one that points up, so it's positive. These two point down, so the tendon minus the center of gravity minus the bone force equals 0. And so the tendon force is the center of gravity, which the weight of the center of gravity, which is 4 times 9.8, minus the force of the bone, which I'll use as the unrounded number, so 156.8. And, oops, I shouldn't have a minus there. I should have a plus there. So I need to add both of these to the other side to get that this equation solved for Ft is force Cg plus Fb. So this here, both of these numbers are put in there as positive numbers. And I got 196 newtons, which rounded to 2 sig figs, I need to write in scientific notation because I can't write 200 newtons. That only has 1 sig fig. So I'll write as 2.0 times 10 to the second newtons for 2 sig figs. Okay. Oh man, I have been working all of this. Well, not quite all of it. Much of this you couldn't see, so I'll put that up there. So on the posted solutions, I've done this a little bit cleaner, I guess, but I also on the posted solutions drew the force of the bone as pointing up. So you can see how it would be different if you were to do this a different way. You'd get the same answer, just slightly different work.